Anyway, we're going to start chapter 15, and we'll cover it both today and Wednesday. Again, a reminder, that material will not be on Friday's exam. That'll be in exam number 3. And I think, as I think I might have said, I suppose that I was thinking that I didn't want to put the exam on Wednesday. I mean, I could. Really, we could have had it today. I just didn't want to push it. So I guess that's what I was thinking. I just prefer to put an exam on Monday or Friday if I teach Monday, Wednesday, Friday. It's like on Monday you have the weekend to study, and on Friday you take it and you go home and get it over with. So yeah, I'm here. I'm getting the feedback that people can hear me with this microphone, so I'm wary of changing anything. That being said, now first of all, I'm hoping you can all see the class notes. Since I'm going to start with there, I'm probably going to go back and forth between the class notes and the whiteboard, because I'm of course going to draw some structures as per usual. But our focus on lipids, which is basically a class of biomolecules that are largely water insoluble. And we're just going to look at them in terms of the functional groups that are present. I think that's something we're going to be able to understand. And of course, in terms of their reactivities also, the things you can expect that these molecules might do. Certainly, I'm not going to be real excited about you guys memorizing any particular lipid structures. There might be some smaller molecules that might be useful. Yes, and I think there is still homework, but I'm not sure that it's for grading. So I really don't know what it means if there's a due date, but it's not graded. Because I think the chapter 18 owls, and I think the same is going to be true for chapter 15. So if it says it's not graded, then it's not graded. If it doesn't say it's not graded, then it's graded. That's always going to be the case. But a lot of these biochem chapters, they give me very few questions that I can actually share with you. Most of them go very far afield and are not things I want you guys to focus on. And the same thing in chapter 15 too. We're going to steer clear of biological function and molecular biology topics, not because I think there's something wrong with those topics, but because I don't think they belong in an organic chemistry class, and I don't consider myself qualified to teach you guys on it, much less examine you on it. So we're going to focus on structure and reactivity, just like we always do. And I hope to convince you that once we understand these lipids structurally, they're very approachable, and there's really nothing too terribly surprising about how they behave. So let's see, I think we're, as in my usual manner, I'm going a little bit out of order in the class notes. And I just want to double check, you guys I'm sure you guys in chat can see the class notes, right? Because I see the green border around the class notes. So what announcements I made? There's an exam Friday, and homework that is graded is graded. Homework that is not graded is not graded. Basically, that's all I said. And of course, chapter 15 will not be on the exam. Oh, good, you can see the notes, thank you. So I'll probably be going back and forth between the class notes and the whiteboard when I'll have a few things to draw. So I guess, yeah, these all kind of go together. Fats, oils, triglycerides, waxes are very closely related. And we'll talk about soaps a little bit. And this is interesting. You've got a section in your book about synthetic detergents or syndets. I had never heard about this before. Yours is the first textbook that covered it, so it's new material to me also. And I'll go through that as well, just so that we can understand that. And after we get through those topics, we can look at the reef session I made. Again, it's not for points. We're just taking attendance today. But I think it's a worthwhile practice problem based on nucleic acids, which we've covered. That's good. That will, of course, be exam material. And then if there's still time left, if you want me to work some problems, we can do that. Otherwise, we'll call it a day, and I'll see you on Wednesday. That's kind of like my plan for today. So let's start then with fats and oils. Those are among the more common classifications of lipids. Again, we expect fats, oils, these things to be water insoluble. You've seen butter floats on water, whether or not you melt it. Oils, of course, you're familiar from your salad dressing or what have you. And then waxes, I think you're also familiar with in general. You've heard of beeswax. There's also synthetic waxes, and all of these are very similar structurally. The fats and oils are often called fatty acids, and fatty acids are quite simply long-chain carboxylic acids, period, full stop. If you understand what a carboxylic acid is, you know everything you need to know in order to understand the fatty acids that we find in fats and oils. And, you know, there are some that are pretty common. I sure don't care if you memorize these structures, of course. I don't care if you memorize the structure of oleic acid and linolenic acid. And, anyway, we were talking about fatty acids, and we said there's simply, today's the last lecture. Today's lecture is not on the exam, neither is Wednesday. So we're done with exam material. And yeah, it's like I was saying, I could have put the exam on Wednesday or even today. I just didn't want to push it that hard. And I would rather not put an exam on Wednesday. Sometimes it's hard to avoid and I just can't help it. But I think Friday is good because you take it, you get it over with, and you go home for the weekend. So, and Monday is also has its strong points. At least you get to study over the weekend. But so no, there's chapter 15 will be on exam 3. It's my birthday. Well, happy birthday. You wouldn't want an exam for your birthday, I suppose. Anyways, back to fatty acids. So, you know, all you really need to make a fatty acid, just, you know, make a long chain as long as you feel like, and put a carboxylic acid group on it, and you will have yourself a fatty acid, just that simple. And we could even figure out what it's called if we really wanted it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, they usually have an even number of carbons. So this would be hexadecanoic acid. So 16 carbons. That would be an example of a fatty acid. That would also be an example of a saturated fatty acid, meaning that the carbon chain, by saturated, we mean that the carbon chain has as much hydrogen as it possibly can have. There's no multiple bonds here. And as you're probably aware, your saturated fatty acids are the ones you'll more likely find in solid fats, your Crisco, your animal fat, your butter, things like that. Unsaturated fats, what that means is that there's at least one carbon-carbon double bond along the chain. And again, I don't happen to have any particular unsaturated fatty acids memorized, and I wouldn't want you to either. But one thing that's kind of interesting about them is that for some reason, fats or unsaturated fats that occur naturally, for some reason, the double bonds are always cis. Again, at least the ones that occur naturally. That's kind of counterintuitive, I would think, right? Because we're used to the trans double bond being more stable. Yet for some reason, the ones that are naturally biosynthesized in plants and animals have cis double bonds. I couldn't really tell you why, but it's true. So this would be an example of an unsaturated fat. And some of them are polyunsaturated fats. You may hear these terms in commercials, you know, and those are going to be the ones in fats of plant origin. That's your olive oil, your peanut oil, sunflower oil, all that sort of thing. And so what happens is the presence of these double bonds makes it kind of more difficult for these molecules to clump together. And so that raises their melting point. And that's really what we mean when we say something. Wait a minute, did I say that right? Hold on. I think I might have just lied to you. I don't want to lie to you guys, so let me double check myself. Let's see now. I did lie to you. The lower the melting point of something, then the likelier it is to be a liquid at room temperature. If something is a liquid at room temperature, like, oh, I don't know, water, right? Then we would expect the melting point to be lower than room temperature, i.e. 0, right? And of course, room temperature Celsius is right in about the low 20s Celsius, usually around 23 or something like that. And some of these liquid fats, well, they might have melting points that are like -10 or -50 or something like that. Whereas if you look at the melting points of your solid fats, those are going to be higher. Those are going to be like +40, +50, something like that. So you need to heat it to a higher temperature, a temperature above room temperature, in order to get them to melt. Again, it's easier to get these things to be in the liquid state because they don't clump together as well because of these double bonds. Are saturated or unsaturated fats liquid at room temperature? It is unsaturated fats that are liquid at room temperature. By and large, these are what you're going to find in your vegetable oils. I'll write all that down. Just give me one moment. Unsaturated, usually liquid. At room temperature. I'm going to go R period, T period for room temperature. And this type of fatty acid is a saturated fatty acid. These are going to be the ones in your fats of animal origin in general. So this is a saturated fatty acid. And that's usually solid at room temperature. I'm sure occasional exceptions are out there, but I think you'll find in general these things are true. And once we understand what fatty acids are, well, then we understand everything we need everything we need to know in order to understand what a triglyceride is. So let's see, these are fatty acids. I have to remember to put up headings, words, definitions, things like that. I often forget to do that. I have to get better at that. So these over here are examples of fatty acids. And again, I don't want you memorizing particular structures. That's not the point here. What you should aim for is to be able to distinguish one type of lipid from another. That's the main thing we're going to do. And that's what it says in the class notes. It's pretty clear what you have to know there. Good, so much for fatty acids. What about triglycerides? You might have heard this term if you go to the doctor for a checkup and get your blood drawn. This is one of the things they check the levels of in your blood work. So triglycerides, they're also called triacylglycerols. There you go again. Two words that mean the exact same thing. And I could probably even think of a third word that means the same thing if I really put my mind to it. Triacylglycerols. And I put the definition of triacylglycerols in the class notes. So you'll forgive me for not writing it down here word for word. It's in your class notes. But triacylglycerols are simply triesters. We know what esters are, right? We know what an ester functional group is. If not, you might want to review that because you're going to need to know all the functional groups all term in order to make sense of the class material. But they're triesters of a triol called glycerol and 3 fatty acid molecules. So first of all, we need to know what glycerol is. And I mean, if you had to memorize a molecule, glycerol is not so bad. It shows up a lot. So wait a minute, let me do this. So triglycerides include glycerol. By the way, glycerol, you might have heard of something called glycerin. Same difference, exactly the same molecule. Glycerol is 1,2,3 propane-triol. So it's a molecule with 3 carbons, each of which has an OH group on it. HOCH2, CHOH, CH2OH. That's glycerol. And it shows up a lot in all kinds of consumer products for both internal and external use. Glycerol, for instance, it's very benign. It's pretty much completely non-toxic. Again, I wouldn't go drinking gallons of it. That might not be a great idea. But glycerol is quite non-toxic. You will find it in lots of soaps because it comes along with the triglycerides that they use to make the soaps, for one thing, as we'll see a little bit later from now. But also, it's nice on the skin, you know, so that's why you'll find it in bath products. Glycerol also has the nice property of being sweet. Maybe not quite as sweet as sugar, but it is sweet. And so you'll find that in lots of foodstuffs. If you think of those hard candies that have like the soft center, they have glycerol in them to keep it soft. So like it's quite harmless, again, within reason. Please don't everyone go out and buy a gallon of glycerol and drink it, but it's quite non-toxic. And triacylglycerols or triglycerides are just what you get by mixing 3 fatty acid molecules with glycerol and forming 3 new ester functional groups. So again, if you've forgotten what an ester functional group is, please review that in chapter 1. You're going to need to know that in order to understand this. But if I were going to draw a typical triglyceride, we could even take, say this, we could even use this compound, this 16-carbon carboxylic acid. And if you made a triester of glycerol with 3 of those molecules, I'm even going to abbreviate the chain. I'm going to do CH2 taken 14 times. CH3, much easier to write that way. Some things actually are easier when you don't use line and angle drawings. So that's the first carbon. On the second carbon, we're going to have, so this is an example of a triglyceride we're doing here. And again, please don't memorize this structure. That's not the point. But we would put another fatty acid residue over here. This will be our 14 CH2s. And then CH3. And then last but not least, we'll have another carbon with an oxygen attached and another ester from a fatty acid molecule. And I'm making all of these 3 fatty acid residues the same. They don't have to be, but they can be. But when you get your blood tested for triglycerides, they're measuring for the presence of molecules of this type. These are triesters, so here's an ester functional group, here's an ester functional group, and here's an ester functional group. They're triesters of glycerol, which is the same molecule, so you imagine removing the 3 H's and putting on carboxylic acid residues over here. Acyl groups, I guess you could say. We've defined that term acyl already. That definition is in your class notes in chapter, try 4, because we talked about acylation of benzene and aromatic compounds. So it's the same definition as there. So this is typical for what a triacylglycerol or triglyceride would look like. And this is one of the major ways that fats are carried in living systems. There then are, of course, biological reactions in the cell that hydrolyze the esters and give you the fatty acids back. And again, I'm not really going to focus on biological function, but if you take biology later and are concerned with things like biological function, I think it'll really be a big help to you to understand the structure of these things. So they're not totally mysterious to you. But that's an example of a triacylglycerol. What about waxes? Let's do waxes. And then we'll talk about soaps, because both of those are going to be related to triacylglycerols, to triglycerides. Make sense? Any questions about fatty acids or triglycerides? All right. Well, what about waxes? Waxes, and the definition's in the class notes again, but a wax is basically a long chain ester of a long chain carboxylic acid or a fatty acid. So they tend to be things that look kind of like this. Again, there could be this long carbon chain, and then you'll have the acyl group from your carboxylic acid. But instead of OH, there's going to be another long chain over here, maybe something like this. So all waxes look something like that. They're long chain esters of fatty acids. By long chain, I mean long chain as opposed to like small esters, like a methyl or ethyl ester. So they're what you get when you condense a long chain alcohol with a long chain carboxylic acid or fatty acid. So let's say long chain esters of fatty acids, which are in turn, we've already defined that, which are in turn long chain carboxylic acids. So and I mean, I actually made those chains probably, if anything, a little too short. You know, these might have 30 or 40 carbons each. So they can be really, really long chains. And whatever kind of wax you might find naturally occurring is going to have a structure something like that. Certainly these wax will look something like that. And so the way you know the difference between a wax and a fatty acid is whether it's a long chain ester over here or just OH. OH alone will be fatty acid. And again, you know how AL will be, even if the questions are not graded. Don't expect that the O of the OH will always be on the right. They might turn the molecule around on you, right? Be prepared to recognize any of these no matter which direction it's pointed. So don't memorize that it always goes on one side. It may or may not. You know that AL will be evil whenever they possibly can. So not me, of course, heavens no. I would never do that to you. Well, maybe a little. Anyway, so much for waxes. Let me go back to your class notes, if I may, and just make sure I'm not missing anything overly important. So we've got, oh, of course, I forgot to talk about hydrogenation of vegetable oils. So you'll recall a while ago, I gave the example of some unsaturated fatty acids. I drew one with a carbon-carbon double bond in the chain. And I mean, there could be 2, 3, 4 carbon-carbon double bonds in the chain. And again, naturally occurring unsaturated fatty acids will have cis double bonds. But we already learned in chapter 3 that you can treat an alkene, that is a carbon-carbon double bond, with hydrogen. Hydrogen usually in the presence of a metal catalyst like palladium or platinum or nickel, one of these ones. And the H2 will add across that carbon-carbon double bond, won't it? And it will reduce it to a single bond, and each of the 2 formerly alkene carbons will get another H on them. So that's in chapter 3, if you've forgotten that reaction. You'll still have to know about it in order to understand this idea. And so you've probably heard of the process of hydrogenation of vegetable oils. If you're the type to read food labels, which I kind of wouldn't mind if you were, then there are a lot worse things you can do for yourself than reading food labels carefully. But you might have seen the phrase partially hydrogenated vegetable oil or partially hydrogenated soybean oil. Well, what that means is that they will treat these long chain fatty acids with not quite enough hydrogen to reduce every single last double bond in every single molecule. You know, it will only reduce some of them. And the reason they do that is they want to get a mixture that has the right properties that they want. You know, maybe they want the properties of the mixture to be such that now they can make whatever that stuff is that's in the middle of a Twinkie, just as an example. And so that takes lots of trial and error on the part of food companies. But the other problem with only partially hydrogenating it as opposed to completely, you know, excess of hydrogen, the other problem is there's a chance that rather than reducing the double bond to a single bond, you will simply isomerize it from cis to trans. And there you go, those are your trans fats. You've probably heard of those. They're the bad actors. Only because we don't have good, efficient systems or biochemical pathways in place to metabolize them. So they cause lots of wear and tear. It generates lots of radicals, which are bad for you. I think we've already covered that, how radicals are getting in there and damaging your DNA. It's really not a pleasant scene. So my understanding is that they have ways of removing the trans fats from the mixture. So you'll see that on food labels too, no trans fats. And I think we can largely trust that. But I just wanted to make sure I talked about that. And of course, when you hydrogenate these vegetable oils, well, then you're going to drive their melting point up. You're going to make them likelier to be solid, or at least more so solid than before, at room temperature. So, and again, they just want to get whatever food product has the right properties. I'm not an expert on that. I'm no food scientist. But I trust that there's, protocols for doing all this kind of thing. So I did want to be sure to mention that. And waxes we've already covered. We mentioned triacylglycerols. Oh, and here we are about unsaturated fatty acids. So this is just going to be just an alkene reaction. Just remember that what you might want to put there, just as a reminder, is that you can take any alkene and treat it with hydrogen in the presence of some transition metal catalyst. Usually it's one of these coinage metals, like palladium, platinum, or nickel. Those are the most common ones. And you will reduce the double bond to a single bond, and each of the formerly alkene carbons will get a new hydrogen attached. So here I'm giving you a visual aid to help you remember that reaction. We talked about that in chapter 3 when we discussed alkene reactions. So if you need to review that, please, by all means, do so. And the only difference is we're just going to do that to one of the double bonds in a fatty acid that has one or more double bonds in it. And then we discussed about partial hydrogenation. Means that we don't hydrogenate every single last one of the double bonds in every single last molecule. Again, in order to get some sort of foodstuff that has properties that we want. And that's basically it, but I thought I'd better put that down. You can put that in that space in the class notes to remind yourself what hydrogenation of a double bond means. Good, let me just head back over here. I just want to make sure I'm not missing anything too important. I think that will do in term until soaps. So yeah, absolutely. Let's do soaps, both solid and liquid soaps, and then let's also talk about syndets, synthetic detergents. It's like I said, I learned something from your book. I did not know that. I thought it was pretty interesting. So let's see. So before we do that, any questions on any of these classes of compounds, or on hydrogenation of unsaturated fats, or again, I don't think I'm going to be too much help in terms of particular food products or things like that, but I can tell you in general, like we did, what hydrogenation of fatty acids is for. I think we got the frowny face from maybe someone isn't so excited about these, whatever that stuff is in the middle of a Twinkie, which I get it. So everyone clear on that so far then? And again, focus on what we cover in class. Focus on being able to tell one lipid from another. If you're given structures, you can go, that's a triglyceride, this one over here is a phospholipid, and over yonder is a terpene. That would be a good sort of thing to aim for. That's what we're, can you go over the main idea of hydrogenation? Well, what we said in chapter 3 was that if you take any alkene, so you can put whatever you want in those bonds, it doesn't matter, and you treat it with hydrogen in the presence of a metal catalyst, what it does, I even gave you a step-by-step method back there. Step 1, turn the double bond into a single bond. Step 2, put H's on each of the 2 carbons that used to be involved in the alkene. That's what happens in hydrogenation of an alkene. But it was in chapter 3 that we discussed this reaction. That was one of the addition reactions to alkenes. Is that kind of what you meant? Hopefully that answers your question. The mechanism of the reaction is not well known. I certainly don't know it. Wouldn't expect you to either. Good. Back then to class notes. If I just, well, I mean, I should see this. So we're going to do solid and liquid soaps, and then come back to your class notes for syndets. That's at least my plan. Good, so back to the whiteboard. Let me clear all that. So how are soaps made, or how did they used to be made anyway? Soaps are basically what you get when you saponify or hydrolyze triacylglycerols. So let's go back to a typical triacylglycerol. I'll draw a structure similar to what we had before, except if you don't mind, I'm just going to put R1, R2, and R3 for the carbon chains that are in the triacylglycerol. So this is not a soap that I'm drawing. I'm just drawing another triacylglycerol, or triglyceride if you like. But I'm just going to call these chains R1, R2, and R3. They can be either the same or different. It doesn't matter. R3. So this is, of course, a triglyceride or triacylglycerol. It's the triester, tri because there's 3 ester groups, the triester of glycerol, which again is 1,2,3 propane HOCH2, CHOH, CH2OH. And we'll just esterify that with 3 fatty acid molecules. And again, those 3 molecules can be the same or different. So all triglycerides are all triglyceride, wait a minute. Triglyceride or triacylglycerol. Use whichever term you prefer. And so that's what a typical triglyceride will look like. Well, we haven't really covered the reactivity of carboxylic acids, except that we know they're a little bit acidic, and esters yet. I actually think that might be the very last chapter we do this term. I think that'll be chapter 10. I could be wrong. So where is glycerol connected in this triglyceride? The glycerol is in here. That's the part that comes from glycerol. If you go back in your notes and look, you'll see glycerol is this, except with H's on the O's. And the reason we take the H's off is to put on these 3 carboxylic acid type groups, these 3 acyl groups. And again, the word acyl we've defined already. We defined that in chapter 4. So this is from glycerol. Does that make sense? Everyone okay with that? So when we make a soap, or at least when we used to make a soap in the old days, down on the range type of thing, what they would do is they would treat it with lye, which is sodium hydroxide. Oops. Or KOH, which they would call caustic potash. Lye, also called caustic soda, soda for sodium, potash for potassium. And you can use either of those strong bases. And they would basically drop the triglycerides into water with a bunch of lye and just cook it, literally. There used to be a famous Gen Chem experiment where people would make their own soaps, except it's kind of messy. It's not impossible that you did it in a high school chemistry lab or even in a Gen Chem lab. You may or may not have done that. But in the end, what you'll wind up getting is glycerol back, which again, often they actually leave in the soap. Since it's completely benign, it's even good for your skin. So they may or may not remove the glycerol from the soap, but that's glycerol. If you go back and compare, that's the same structure. And you will also get basically 3 fatty acid molecules. except they won't really be fatty acids, will they? They'll be the conjugate bases of the fatty acids. So you'll get this plus the R2 fatty acid. I really should have made, you know what, I'm even going to do that. I'm going to take the opportunity to go back and just make all of these R's the same. Though they don't have to be. But I think just so we don't have to write quite so much. So you'll get 3 fatty acid molecules, and they'll all be the same if all of these R groups are the same, or they'll be all 3 different if all of the R groups are different. It doesn't matter. Either way, you'll get a soap. And of course, along with this anion, you'll get either a sodium ion or a plus or a potassium ion. Whoa, struggling here. Or K plus. According to which hydroxide you used, whether you used sodium hydroxide or potassium hydroxide. And it's these fatty acid salts. These things are what we mean by a soap. And again, sometimes they leave the glycerol in there, sometimes they don't. But it's these fatty acid salts that are what we mean when we refer to soaps. And so, yeah, I think that's about all I need to say about that. The way these things work, as I think you can imagine, this end of the molecule is very, very water soluble because it's an ion, right? Ions love to dissolve in water. This part of the molecule is not water soluble at all. And so the end result, again, I am no biochemist or biologist, so please forgive me for, I'm sure I'll screw this up. But the idea is very much like a cell membrane, actually. Don't they have this, this two-sided type of thing, the end that's very hydrophilic and dissolves in water, and the end that's very lipophilic and forms the other side of the membrane. Same thing. And so this side of the soap molecule will dissolve in water. This side will glom on to all these grease particles, you know, all the dirts or whatever that, well, we'll get to phospholipids are slightly, oh, well, that's true. Yeah, it is strongly related to phospholipids. We'll cover phospholipids the next time. They are also really closely related. Is the Na attached to the oxygen? I would say no, this is an ionic bond, right? So there's no actual electrons shared. So the oxygen is a full minus charge and the sodium or potassium is a plus charge. So this is an ionic compound, right? There's no actual bond there. But whether it's a sodium or a potassium salt, you've got yourself a soap. In general, your solid soaps tend to be sodium salts for some reason, and your liquid soaps tend to be potassium salts. And that's in the class notes, just in case you're wondering about. I would expect that, I mean, to the extent that they don't use synthetic detergents, I would expect to find largely potassium salts in those liquid pump soaps that you know, that were impossible to get in the supermarket for quite some time. Well, they're back now, largely. And then if you like a bar of soap, I wouldn't be surprised if that was largely sodium salts. They tend to make solid soaps. So that's all fine as far as it goes. But the reason why this is the old school way of making soaps, and we have some better methods now, I would say, is because the reason why this is a problem is in those places where you have very hard water. And you've got, you know what hard water is, it's got lots of metal ions in the water. And the trouble is these ions that come from these metal ions like iron +2 or +3 or copper +2, you know, calcium to some degree, and other of these other both main group and transition metals. These things are stupidly insoluble when they get in contact with these carboxylate ions. The sodium and potassium salts are quite water soluble, but when these are paired up with other metal ions, it's very insoluble. And so this is your bathtub ring, and this is your gooey rings on like shirt collars and whatnot. That were the stuff of commercials for laundry detergents and such like. So again, unless you have either a water softener or just an area where the water is quite soft, that's a significant problem with these older kind of soaps. So they found another way of making soaps, which is in your book. And like I said, this is the thing that I learned from reading your textbook, because I did not know what the structure of synthetic detergents was. I didn't realize it was significantly different. So what you do instead, and again, I'm taking this directly from your class notes, I'll just show you. It's not a reaction that I was familiar with, but it's in this paragraph here. So what they do is they take those same triglycerides and they treat it with copper chromite, which is not something I had heard of before. I don't know how much I care that you memorize that. It might be nice if you at least recognize that, oh yeah, that's that stuff that they reduce triglycerides with. So let's go back to our whiteboard. So it was Cu2, I've forgotten already. Cu2Cr2O5, good, got it. And I bet they have to heat it pretty strongly at the same time, Cr2O5. This is actually a reducing agent, and so it's going to not only cleave off the glycerol, you'll get that too, which again, they might or might not separate out. They might leave it around or they might take it out. It's not like if they could recover the glycerol, it certainly could be used for any number of other things. But what you get then, instead of 3 fatty acid molecules, you get 3 long chain alcohols. It reduces the carboxylic acid all the way down to a primary alcohol. So you'll get 3 of these molecules. So again, notice these are not carboxylic acids, these are alcohols. And it's from these that you make synthetic detergents. The first step is that they treat it with sulfuric acid of all things. And this will make alkyl sulfates. CH2O. Instead of OH, we're going to put a sulfate group on it, which looks a lot like this, OH. And then they treat this with a mild base, or, careful reaction with a little bit of aqueous sodium hydroxide or something. Or some other mild base like that. And instead of 3 alkyl sulfates like this, instead of getting the free sulfonic acids, you get CH2O, S double bond O, double bond O, O minus. That will deprotonate the sulfonic acid. And I guess presumably you would then get the sodium salt of that. Or if you used KOH, it would be the potassium salt. Whatever the counter ion, the metal ion is, these are syndets. These are synthetic detergents. And these do not form those nasty insoluble rings, or they still remain quite soluble even with some of these nastier metal ions like copper and iron and so forth. So any of the consumer synthetic detergents probably look something, sorry, minus charge, probably look something more like this. So I thought that was interesting. Like I said, I did not know that until I read your textbook. And that is actually a fairly good place to end. It also does not leave me with enough time to show you my, the little exercise I'd planned. Oh, well. Basically, I was just gonna draw a nucleotide with you guys. We did that in class too, but with 2 minutes left, I really can't fit that in. So anyone want to end with any questions then? No, you just want to get out 2 or 3 minutes early, which is fine. I can live with that. 10 minutes, I'd be a little embarrassed. 2 minutes is fine. Okay, so nap time, yeah. So I heard that, amen to that. So in fact, we will get to The person asking about their phone not working, yes, drop me an email. Do we need to know the steps to get Syndex? I would say so. I mean, again, I don't really care if you memorize Cu2Cr2O5, but it would be great if you recognized it. The other two reactions really are nothing surprising. We'll pick up here next time, and someone mentioned phospholipids. We'll start with things like that next time, and we'll finish up on lipids. So other than that, have a great day. We'll see you Wednesday.